Section 1.2 is about row reduction and echelon form. That's E-C-H-E-L-O-N, echelon form. That's how it's pronounced. A matrix M by N, that's M as in Mary, N as in Nancy, is called in row echelon form if it satisfies three conditions. And the conditions are as follows. Any row consisting all zeros, that means if you find a row which has nothing but zeros, it has to be located at the bottom of the matrix. Remember, this is like the top of the matrix, and this is like the bottom of the matrix. So they have to go all the way down. And let's say this is M by N. Okay. The first non-zero element in any non-zero row, it has to be 1, and that one has a name called leading one. In other words, in each row, as you go from left to right, the first non-zero element has to be 1. The leading one, so it's called leading one, the leading one of any row has to be to the right side of the leading one in the previous row. So if the first row, like for instance, has a leading one here, the second row has to have its leading one to the right side. It doesn't have to be immediate right. It could be right here as well, as long as the leading one in the next row is to the right side of the what? Leading one in the previous row, but not necessarily what? Immediate right. So those are the conditions. So with that said, let's see if we can identify if these guys are in row echelon form or not. This guy is in row echelon form. As I go from left to right, the first non-zero element is 1, so that's leading 1. As a matter of fact, that's called pivot position. And as I go from left to right, the first non-zero element is 1, but that one is on the what? Right side of the one in the previous row. So that's leading 1. And if I go from left to right in third row, the first non-zero row element is what? 1. And that's way to the right side of the row, which happened to appear in row 2. So in other words, notice it doesn't have to be immediate right, as long as it's on the right side. So we good. This pretty much satisfies all those conditions. So we say, hey, this matrix is in row echelon form. What about this guy? Well, the first element as you go from left to right is 1. Everything else is 0. All the conditions are satisfied. What about this guy? Well, the leading one here is 1, here is 1, but this one is in the wrong spot. It's supposed to be on the right side, so this is not in row echelon form. This guy is not in row echelon form either because 0, 0, 0 is supposed to appear at the bottom of the what? Matrix. It's appearing in the second row. This guy is not a what? Row echelon form because yes, the first non-zero element in first row as you go from left to right is 1. But look at this. This guy is in the wrong spot. Do you see it? This guy is in the wrong spot. So therefore, this is not what? Row echelon form. This guy is. It satisfies all the conditions. This guy is not because this one is in the wrong spot, supposed to be on the right side of the one from previous row. This guy is definitely not what in row echelon form because you don't even have a 1 here. Remember the first non-zero as you go from left to right to any row supposed to be 1, not 2. Then we have something called reduced row echelon form. So these are called row echelon form. Then we have something called reduced row echelon form. Reduced row echelon form is a matrix which happens to be already in row echelon form, but any column which has leading 1, everywhere else in that column is what? Has a 0 everywhere else. In other words, let's say this guy is in row echelon form, correct? I have a leading one, what? Let's say, let me pick one which, like, let's say this guy. This guy is in row echelon form, correct? So to put this in a reduced row echelon form, I'm supposed to have what? Any column which has a leading one, everywhere else, it's supposed to be what? 0 in that column. Do you all see it? Like, let's say I have, let's say, leading 1 here, so everything else has to be 0. So that's considered to be what? Reduced row echelon form. Do you all see it? So whichever the column has a leading 1, in that column, every other element is supposed to be what? 0. So there you have it. Okay, so using elementary row operations, we can reduce a matrix into row echelon form and hence find its so-called rank. And the rank of a matrix is denoted by rank of the name of the matrix, which is a number. In a minute, we'll see what rank is. What is a rank? Is the number of non-zero, that means not all 0, non-zero in any row echelon form of a matrix is called rank of the matrix. And the notation is this guy. So what does that mean? That means, let's say you have a matrix, let's say 2, 1, 1, negative 3. First of all, this is definitely not in row echelon form. Question is, put it in row echelon form first, and then find its rank, and then take it further and put it in reduced row echelon form. So remember, we're supposed to use elementary row operations. What are those? Just to remind you, we can exchange 2 rows. We can multiply a row by any non-zero scalar. We can also take a multiple of a row, add it to a different row. So with that said, suppose this is row 1, which I'm going to call it R1. This is row 2, I'm going to call it R2. First thing I did was exchange or switch row 1 with row 2. Remember, that's still considered to be elementary row operation. So when I did, I got a 1 here. That's all. That's really what I needed, to have a 1 here. The next item is to force this guy to be equal to 0. So the minute you get a 1 in any column, make sure what? The elements below that leading 1 is 0. How do I force this guy to be 0, the 2 to become 0? Take a multiple of leading 1, which is like negative twice of 1. Add it to 2, you get 0. Remember, we always take a multiple of the leading 1, add it to the next row, not the other way around. Because if you do it the other way around, you may lose your 1. So here, take a multiple of the leading 1, which I took negative 2 twice of 1 plus 2. So that's negative 2R1 plus R2. So I got negative 2 plus 2 is 0. Negative 2 times negative 3 is 6. 6 plus 1 is 7. I got my 0. Now I'm supposed to force this guy to look like a 1. What do? I don't say divide, because division is not defined. So we say let's multiply row 1 by 1 over 7. And when you do, lo and behold, now the matrix in row echelon form. As you go from left to right, the first non-zero element is 1. Those are called leading 1. And the leading 1 in row 2 is to the right side of row 1. And I don't have any rows of 0 to worry about. So the number of non-zero rows in any row echelon form determines the rank. Notice neither of these rows happens to be all 0. Therefore, the rank of this matrix is 1, 2, because we have 2 non-zero rows in row echelon form of the original matrix. Same thing goes for this guy. So this is R1, R2, R3. Remember, this is 2 by what? This is 3 by 3 matrix. So it's a square matrix. All right. So we like to put this in row echelon form. So the way I did it, I immediately switch what? R1 with R2. This is the notation for switching, double-headed arrow. Okay. So why did I do that for? So that way, in the next step, I subtracted what? R1 from R2, so I can get a 1 here. Okay. So now what I did, in the next step, subtracted R2 from R3. So I got 0. Then in the next step, took what? Twice of R1, subtracted from R2. So I got 0 in this. Remember, the minute you get a leading 1, the objective is to force the what? Elements below that leading 1 to be 0. So as you can tell, the next item is to make this guy a 1, correct? What did I do? I kind of first, before I do that, I switch these guys so that way I can have a -1 as opposed to -5. Then I multiplied R2 by negative, and there it is. I got my 1. So the element below 1 for row echelon form has to be 0. So I need to force this guy to change it to 0. So what do? I take a multiple of this leading 1 and add it to this. In other words, go 5 times 1, what? Plus -5. So when you do, lo and behold, -5 disappears, you get 0. So now the next item is to force this guy to be 1. So take 1/23 of R3, and lo and behold, you got your row echelon form. And because once again we have 3 non-zero rows, so the rank is 3. Now if you take this one step further, and wherever you have leading 1, change everything else in that column to 0, that would be called reduced row echelon form. And that's the acronym is RREF, whereas here is REF, row echelon form. This is reduced row echelon form. Okay, so with that said, so what do you say? We kind of try to solve what? System of linear equation. The methods of solving system of equation using matrices. One method is called Gaussian elimination, which is like putting the augmented matrix in row echelon form. Okay, and then plus we need to use something called back substitution to find the solution. Okay, the solution. However, we also have Gauss-Jordan elimination, which is like what? Put the augmented matrix in reduced row echelon form, and then immediately you can find what? The solutions. There is no need for substitution. Even though this guy is kind of like gives you directly the answer, but it takes more work. So if we were going to write a program for computers to execute, so this guy has more steps than this. So in real life, we use Gaussian elimination most of the time. So let's see what happens. Keep in mind, when the number of equations matches the number of variables, so you have same number of equations as you have variables, the possible solutions are as follow, correct? So these are like what? Possible solutions. That's for which case? Case 1. What's case 1? Case 1 is what? Is when the number of equations matches the number of variables. For instance, you got 3 equations. Can you all see it? Remember, the problem is solved. And you have 3 variables. So solve means what? Find x1, x2, and x3. And usually the answer shows up as order triple, like x1, x2, x3. And S stands for solution. This is how we write the final answer. So let me show you how Gaussian elimination compares to Gauss-Jordan. Watch this. Suppose I want to do this by Gaussian elimination method. So in other words, I need to find my augmented matrix, which is what? The matrix of coefficient augmented with the constant. So this guy. Now I go through series of what? Elementary row operation. And at the end of the day, you know, getting this form, which happens to be now in row echelon form. Notice first I took negative R1, added to R2 to get 0. Then I took negative R1 plus R3 to get 0. Okay, I got this. Then I multiplied what? R2 by negative to make this negative 1. So I got my leading ones. I don't know if you guys can see it. Then my next step was force this guy to be 0. So I took 5R2 plus R3. There it is. Then my next step was to force this guy to be 1. So what I did, I took half of R3. There it is. Now this matrix, which happens to be 3 by 4, is my augmented matrix and is in row echelon form. But if you look at the row 3, it reads what? It reads, I don't know if you guys can see it, 0x. Remember, these are the coefficient of the variables. They are not variables. These are coefficients. So this guy reads 0x1 plus 0x2 plus 1x3 is equal to 4. So that means right away, you know x3 is 4. So you got one of the variables. You still got 2 more to go. Now go ahead and read row 2. How does row 2 read? 0x1 plus 1x2 plus 1x3 is equal to 2. Okay, but so x2 is 2 minus x3, but x3 was 4. So x2 is equal to negative 2. Remember, this is called back substitution. So when you put the augmented matrix in row echelon form, you still have one more procedure to apply to find the solution. It's called back substitution. So we're going from bottom to the top of the matrix. Okay, what about row 1? Row 1 is 1x1 plus what? 2x2 plus 2x3 is equal to 2. So x1 is minus 2x2 minus 2x3 plus 2. But remember, I already know what x3 and what x2 is. So I'm going to substitute, and lo and behold, get what? X1 is equal to negative 2. Therefore, we have a unique solution, and there it is. So this is called unique solution. This is one-of-a-kind solution. However, Gauss-Jordan takes this matrix one step further and puts it in reduced row echelon form, so there's no need for back substitution. What does that mean? That means if I take this row echelon form of what? Of augmented matrix, one step further, and wherever I have leading ones, like so, change everything else in that column to 0, I get this. So this is x1, that's x2, that's x3. Do you see it? The beauty of Gauss-Jordan is you can immediately tell off of the final answer, which happens to be reduced row echelon form. Immediately you can tell what the answer is. Notice in this case, x3 is 4, x2 is what? Negative 2, I suppose. And x1 is also equals negative 2. Do you see it? So notice by inspection, I could immediately tell what the answer is because the matrix, excuse me guys, the matrix happens to be in what? In a row, excuse me, in what? Uh, in reduced row echelon form. This is not in reduced row echelon form. I apologize. So let me just quickly fix that. My apology. So this is not quite ready yet. So I needed one more step, which apparently I forgot. So technically at the end of the day, we're supposed to get 1, 0, 0, 0, 1, 0, 0, 0, 1. And then I have, I think that guy was positive 2, if I believe. So this guy becomes what? Negative 2, negative 2, 4. As you can tell now, I can read off the answer directly from the what? Reduced row echelon form of the augmented matrix. Notice every time I have a leading one in any column, everything else in that column is 0. So this guy reads what? X3 is equal to 4, X2 is equal to negative 2, X1 is equal to negative 2. Once again, the solution is negative 2, negative 2, 4. Sorry about that, guys. So I was missing one more step. Apparently, that's incomplete. So this is in reduced row echelon form, and as you can tell, there is no need for back substitution. Once again, I apologize. So the idea is what? So if you, the number of equations matches the number of what? Variables, then there are 3 possibilities. One of them is unique, which I showed you how to find it. The other one is no solution. And then the other possibility is you may have infinite many solutions. So for this, when I put the equation matrix, augmented matrix in what? Reduced row echelon form, I got a unique solution. For this guy, when I put the augmented matrix in reduced row echelon form, as a matter of fact, this is what? Right. It's right, reduced row echelon form. Check this out. The last row reads 0x1 plus 0x2 plus 0x3 equals 1, which means 0 is equal to 1. Because 0 cannot be equal to 1, so there's no solution. Do you see it? So this is how you could tell if you don't have any solution. Notice you got 0 equals 1. So this row kind of tells you, hey, there is no solution. Okay? On the other hand, for this particular system, I put the what? So-called augmented matrix in reduced row echelon form, and look what I got now. I got a row of completely 0 in the 3rd row. So what does that tell us? Notice that tells us you have infinite many answer, but just to say I have infinite many answer, it doesn't quite cut it. Now I have to express those answers. In other words, when you say infinite many answer, does that mean any order triple I pick that would satisfy these equations? No. So notice x1 has a leading 1, x2 has a leading 1, x3 does not have a leading 1. So we call the variable which does not have a leading 1 a free variable. In other words, x3 can be any real number. T can go from negative infinity to infinity. So we're going to let x3 to be equal to the parameter t. So the fact x3 did not have a leading 1, so that's your free variable. Sometimes there are equations you may have more than one free variable, correct? So what you do, now you go back to the equations, to these rows, and say, okay, if x3 is free, that means it could be any real number. So what would x2 be? Well, from row number 2, notice this is 1x2 plus 1x3 is equal to 2. So x2 is what? 2 minus x3, but x3 is free, which is, parameter t, so it's 2 minus t. Here, x1, 1x1 plus 0x2 plus 0x3 is 1, so x1 is a number, which is 1. Therefore, the solution is 1 comma 2 minus t comma t, where t is any real number. So therefore, this is called parametric equation. Do you see it? Just like multivariable classes. I don't know if you guys remember, this would be the parametric equation of a line which goes through what? 1, 2, 0, and is parallel to the vector 0, -1, 1. So the idea is what? The solution is bunch of points, or I should say ordered triples, on a line whose parametric equation is given by these equations. X equals 1, y equals 2 minus t, z is equal to what? T. So this would be something from multivariable courses, and these are called parametric equation of a line. So there you have it. In case if you have two variables, that would be like a bunch of points on a plane. So one variable is a line. Okay, so that's case 1. Case 2 is like, what if you got more equations than your variables? M is greater than n. Those are called overdetermined systems. If you got more equations than variables, possible solutions are either you have a solution which is unique or you don't. There is nothing in between. For instance, check this out. I got 3 equations, correct? 1, 2, 3. So m is 3. But I got only 2 variables. N is 2. So obviously m is greater than n. So either I have a solution or I don't. So if you put the augmented matrix in what? In a reduced row echelon form or echelon form, excuse me, then again, you will run into this problem. Notice the last row reads 0x1 plus 0x2 is equal to 1, which means 0 is equal to 1. You and I, we know that's not possible. Therefore, there is no solution, and usually no solution is shown by this notation, which means empty set. Do you see it? Okay. What if the number of equations is less than the variables? Let's say you got 2 equations, but 3 variables. So in this case, m is 2, but n is 3. In that case, there is only one possibility, and that would be infinite many solutions, rain or shine. There is no unique solution. There is no such a thing as no solution. You always have infinite many solutions. So if you put, once again, the augmented matrix in reduced row echelon form or row echelon form, this is what you get. All right, once again, x1 and x2, they have leading 1, x3 doesn't. So therefore, x3 is free variable. The free variable means what? x3 can take any real number between -infinity to infinity. Now, if you go read row number 2, that reads x2 equals 2 minus 3x3, but x3 is t, so it's 2 minus 3t. And if you read row number 1, x1 is equal to 1 minus x3, so that's 1 minus t, so there you have it. The parametric equation of this solution is 1 minus t, 2 minus 3t, z is equal to t, t goes from -infinity to infinity. Once again, this indicates you have a bunch of points on a line in a space. If you have homogeneous system, meaning instead of constants on the right side to be non-zero, what if the constants on the right side, there are a bunch of zeros? Do you all see it? Those are called homogeneous system of linear equation. What are the possible solutions? Either you have trivial solution, which means nothing but 0. That means x1 is 0, y1 is 0, just like this guy. x3 is 0. That's called trivial solution. Or you have infinite many solution. There is nothing in between. Either the solution is trivial, trivial means obvious, or you have infinite many solution. Incidentally, these kind of homogeneous system of linear equation with 0 on the right side, they are always consistent because they always have solution. Either it's what? Trivial or infinite many. If it is infinite many, trivial is part of it. So there is no such thing as no solution when it comes to homogeneous kind. And that's pretty much is it. And that would pretty much concludes what? Section 1.2. Thank you.